All right, let's go get started with the next part. So we're still in the introduction area, and I've been very pleased to see that some people use the Slido to find out what CBMS stands for, which sorry, I did also not do my due diligence before coming here, but now we all know that it's the Conference Board of the Mathematical Sciences, okay? Very important. I'll check these off, and then if you have other questions, feel free to post there. Now I have it actually open, so maybe I'll go back to this in the end. But I think it's also been working out quite well that you just ask at the spot. I highly encourage that because the course is for you and not so much for me. So we're free to make use of that. Okay, so what I want to do in this lecture is shifting gears a little bit from very like abstract, high level, like motivation overview kind of thing, and to show you a little bit of a survey of what you could build in machine learning these days. So how do you actually build a learning problem pretty much from scratch? What are maybe the nuts and bolts and pieces that will come up later? So it's still solidly in the crash course, quote unquote, part of the course. Maybe something new for you. Maybe some people have seen this already. That's fine. Apologize for that. But then at the end of the day of this lecture, we'll have an optimization problem set up or learning problem set up, and we mostly should feel good about the ingredients. So that's basically the goal. And yeah, neural networks, I mean, they've definitely seen some evolution. So they are not new. They came up in the 50s or so. But now these days, we went from like finite depth to infinite depth. We're going to see we have many more structures that have been proposed, like convolutional networks, transformers. There's a lot more variety in terms of how people have been engineering these networks. So we'll cover a little bit of the philosophy and the structures of that. There are some good readings about these things that we're going to cover today. This is like my top 5. If someone forced me to give only 5 papers or references to read, some of them are huge books. So there's a bit of cheating, but these are, I think, some good things to get more into it. And especially to highlight is the last part. That's Patrick Kidger's beautiful piece of neural differential equations, which is a topic close to my heart, and actually is this PhD thesis that is more or less like a textbook. And it's a very nice piece of work. If you're at all interested in infinitely deep stuff, then that's where you can get a lot of good results from. Okay, so here's the roadmap. So we'll talk about this in 3 steps. So first we'll think about, okay, so how do we connect the dots? Sort of, we have some features, like how can they interact? Then we'll go deep. So then we'll stack whatever we've done a couple of times or infinitely many times. And then in the end, we'll talk a little bit about how do we measure success. This will be for supervised learning because it's simple. I'll also give you a few other options. What could you do in an unsupervised or reinforcement learning regime? And yeah, then we'll have some fun along the way and take questions anytime. So, okay, so layer design is really about defining the rules of how do the features interact from inputs to outputs. So this is probably the first model you may be familiar with. Maybe our baseline is to have a fully connected model. So you have your x as an input vector. You apply some affine transformation, some nonlinearity, and that gives you the y. So the weights that we're learning is the W and the B, so the weights and the biases, and the W is dense. Pictorially, what we have is, let's say we have 6 input features and 4 output features. Then the first output feature depends sort of on all of the 6 input features. So it's a fully connected graph, and it gives you, in this case, like 24 weights and 4 biases. And that has been sort of the early machine learning models that people have come up with, okay? So, and it's still a model that is useful in certain regimes and also sometimes what the analysis is meant for. What these models don't really capture is that the data you feed in oftentimes has some sort of structure. So you don't just have an input vector x and an output vector y, but these individual components, they oftentimes have a meaning, and that meaning may be good to cover in the learning model to give some inductive bias, to get some invariances. So for example, if you have an image, then these pixels, they actually have a logical ordering of some sorts, and they encode neighborhood information. Your model should know about it. A very simple limitation that you see is that in this case, it's not allowed to change the sizes of the inputs. And that may be different or difficult when you want to, for example, do text prediction, like in ChatGPT. Your text size will grow. One user gives you Harry Potter, the other user gives you a Wikipedia entry. So you need to have a model that sort of can deal with both. If you are an operator learner, then you want to have different mesh sizes and so on. So you clearly see that this model will not get you very far in those cases, right? But there are still ingredients of those cases. So yeah, so if you have structure, like you have images, you have sequences, maybe you have graphs, you want to have more tools at your disposal about how to connect the different parts. And the architecture design and how you make your neural network layer really leverages is always one way to build in whatever you know about your problem. So in a CNN, for example, you have the following picture in mind. So you have your image, let's say you have RGB, different channels and 8x8 images, and then you stack a convolutional kernel with this black box on this to compute two output pixels in the Y. So here you go from 3 channels to 2 channels, and like these 2 pixel values are basically encoded by having a linear combination only in that limited field of view. In this little input tensor, if you will, with some convolutions. And if you write this down in linear algebra, then you actually see that the convolutional layer is not just one convolution. The number of convolutions is the product of the input and the output number of channels. In this case, you have matrices. I call them just C for convolution matrix, where each of them gets a stencil, takes an input channel, and their sum is going to be one output channel, right? So this has been breakthrough architecture from LeCun and others, and then over the years, the workhorse in image classification, image segmentation, and any other, like also in voice and in video type of problems. And there are 2 things here at play. So first of all, if you think about this from a computational point of view, all of these convolution matrices, you can represent them as sparse matrices. So you're not a fully connected dense matrix, but you're really sparse. You only look into your couple of neighbors around. And also the weights are shared. So you have a very small number of weights to represent one of these operators. Like if you have a 3x3 convolution, every one of these operators, no matter how many input pixels and output pixels you have, it has like 9 weights or so. Okay, so that's making them quite powerful, because then in principle, your CNN would actually work for images of different sizes. In practice, not so much. I mean, you have to do some work when you increase the resolution to make it like a faithful representation of what you actually want to model. But this is, I think, one leap already from the fully connected architecture. And of course, once you think about this as being a sparse matrix, you could also think about other ways how to represent operators in a more structured way. So later on, we're going to see the Fourier neural operator network. And you could easily think about this as not just a 3x3 convolution stencil, but it could be something like a diagonal multiplication in Fourier space. So this is another way to encode structure of similar shape here. Okay, so CNNs are great for some things, but also they have some limitations. And one of the limitations I want to illustrate here on the right-hand side is the following. Let's say you have this Q-tip example. So you see, I think, 3 different types of Q-tips. So white and black on the tips, white, white, and black, black. And now put yourself into the shoes of a convolutional neural network that needs to assign a class label to each of these objects. And when you try to think about it, then this is going to be quite a challenging problem for a CNN. Because in order to make a decision of what bucket this Q-tip falls into, depends on both ends of the tip. And now you can do a numbers game. You can ask me, okay, how many pixels do we have in an image? and how big can you make the field of view of the CNN? And if you say do 3 by 3 grid size, then you'll have many, many layers until you kind of bridge information over hundreds of pixels. Okay. So that is one of the common issues with CNNs, that they have a very limited field of view. And that is in some sense a feature and a bug, because if it's actually meaningful in your data that you only have local interactions that you need, great. This is a good inductive bias to have. But if you actually need to translate information over long parts of the state space, then you need to be more creative. So you may want to think about, for example, doing an inverse of a convolution has a much bigger field of view because it's an integral operator and so on. So that is a common issue with CNNs. That's why you may want to have them. You can always compensate maybe with more depth, which we'll talk about, but it's something to be mindful of, like what is actually your field of view and how does it grow as you concatenate these things. Okay. So that leads us to a whole different class of models, which are graph neural networks. And in some sense, you could think even about the CNN example as a graph. So what is a graph? So here is one, let's say. So you have a bunch of nodes, 6 nodes or so, and at each of these nodes there lives a vector. Okay. And I could represent this as a matrix, a big X. So you see the 6 rows and 4 columns. Okay. So these are just the stacked weights of the nodal features. And one way to design a network layer now could be as follows. So X is your data matrix. Let's say you have from the left some matrix that connects the features. So it can exchange, like have basically weighted linear sums of the feature vectors. And on the right, you have a feature transformation that basically takes each vector on its own and does some linear combination. Okay, so this is now a new architecture that you could think about. And what this could then do in an example is, so you have your X, so you have this matrix. Usually it's actually, oftentimes it's a symmetric matrix, and you multiply it from the left so that you exchange information or do message passing. And on the right, you have a W that sort of modifies the features, and that gives you new features that you see here in this graph Y. And you can change the number of features. So you can go from 4 features to 3 features. And depending on now, if we think back for the Q-tip example, and let's say maybe the first row here is the one tip and the other is the other tip. Now you could actually, with your M matrix, encode that it's okay to carry the information over that whole part of the space. Yeah? So you could be flexible in making up this matrix. A couple of ways how this is done in practice is that you make M a graph Laplacian, for example. How do you do that? So you see here actually in this picture that these nodes, so not all of them share an edge. That's a feature. Right? So someone, maybe from the context of this application of the data set, decided which pixels can talk to which other pixel. And then also you see this width a little bit different here versus there. So that's meant to encode the strength of the connection. And it could be that that some nodes are more similar to one another. And so basically what you have mathematically is a weighted graph. You have nodes, you have edges, and you have edge weights, sometimes even in edge direction. So this is an undirected graph, but you could encode that as well. And then a common choice for this message passing matrix would be something, for example, like a graph Laplacian, which would smooth out the information vectors across the graph. Okay, and so that is one way, or you have an adjacency matrix where you average all the neighbors. So that's breaking down the whole process of a CNN, where it does both at the same time, because it could actually, the stencils exchange local informations in a 3 by 3 patch. And then their linear combination actually modifies the feature channels too. Here you break this down. You have one part only doing exchanges, the other part doing the feature transformation. And what's a feature of this way of thinking is that now, for example, if you change the ordering of your graph nodes, nothing bad would happen because the graph Laplacian would also change, would be a symmetric permutation of that whole thing. So you basically build in some permutation equivariance. That's pretty powerful, actually, because think about one way that you could use this in computational sciences is you could think about like a finite element mesh as a graph, also a set of nodes with connections, and you can build very unstructured meshes and have models that work on them natively. There are, of course, limitations because, first of all, you have to have some way to design the M matrix. So you need to know which nodes are talking to one another. Sometimes it's natural, like in finite element, it's very natural. But then if you download a social network data set, maybe not as obvious as you may think, and maybe sometimes it's even impossible. Okay. But this is another interesting way how you can build network, like connecting features in this space. So yeah, some advantages. It works for any graph. You have the W is shared across all the nodes, permutation equivariant. Yeah, so in sciences like molecules, there are some works that use GNNs for that, PDE meshes. But what's really missing maybe is what do you do if you don't know anything about the connectivity? Like in a text, for example, you don't know which words relate to which. In the Q-tip example, also not so much. Why? Because the Q-tips, they were rotated. So you don't actually know which pixel is one end versus the other end. So that sounds like a daunting task to kind of make a decision of how you connect these things. And that's exactly what got the CNN into trouble. And that's probably also what's getting at least these types of graph neural networks, which are called graph convolutional neural networks, also into trouble. Okay. So what do machine learners do when they don't know something? They try to learn it, right? And I think one of the big breakthroughs in the last couple of years was these transformers. And they actually also date back to a little bit earlier, but they really were popularized a couple of years ago. And what they are doing, and the way I'd like you to think about it is, let's say we have a fully connected graph. So all features talk to every feature, but you still divide between nodes and feature vectors. So it's not like a baseline model that we started out with. But let's say in principle, you now allow every node to talk to every other node, and then find a way to make the model smartly learn which connections are actually important. Okay, so let's do that. So here's what you do. So again, I made my graph fully connected, still our feature vectors. And now you see here the strength of these ones, again, is sort of indicated by the width. Some connections, maybe this one here seems to be like a highway that is important from 4, 5, 6 are very important, but then 3 to 5 is not maybe too much coupled. So how did the model learn this, or how did the model encode this? There's a bit of linear algebra, but bear with me. So you take your x and you multiply from the right. You have 3 matrices that you're learning, the WQ, WK, and WV. That stands for query, keys, and values. It's like some database lingo, but okay, these are just 3 matrices you multiply with, and they get you from one feature space to another feature space. Okay, fine. We know how to do that. And then how do you measure similarity? What we teach in linear algebra is everything is a dot product in that business. So you basically take the query and the keys, you do a dot product between them, and normalize it somehow for numerical issues, and then you have a score. And that score, so IJ, is large when the features are similar, when the vectors point in similar directions, larger negative when they are completely opposites, maybe 0 if they're orthogonal, right? So now you have a score to work with. It's some simple similarity measure, but it's found to be very effective. And if you could now learn, so the WQ and the WK matrix, they could now encode and learn sort of how to basically transform these vectors into a joint space that captures that information so that that comes out. Okay, great. So that's the first two steps of building an attention mechanism. I think the only other thing we need to make a decision about this sort of having like, yeah, in some sense, it could be nice to have more or less like a convex combination of the different features so that stuff doesn't grow exponentially or kind of decays too much. So here's the last thing, and there's also some very common formula that will pop up every now and then. It's called the softmax transformation. So again, you have your scores now, and now if you actually think about the weight on the ijth edge, which we have here, how about we make these weights non-positive, non-negative, and also make sure they sum to 1? And the transformation to do that in machine learning is a softmax transformation. So you just take the exponential of the score and normalize by the sum. Done deal. So now you can think about them as like basically a probability distribution. So the matrix M that we are building can be interpreted as a stochastic matrix, at least in that one dimension that you apply the softmax over. And now basically you know that every new node will be a convex combination of all of the nodes, all of the other nodes. At some weights maybe 0, at most there can be 1, but they all sum to 1. Okay, so this is called the attention mechanism, and this is one formula to summarize that. So you have basically you apply the softmax row-wise to QK transpose, normalized, and then multiply that with the values. Oh yeah, question? Exactly. So the matrices now, and sorry, they're a little bit hidden here. So this Q, remember, was X times WQ, and the K was X times WK. So those matrices are learned in the end. Okay, and they kind of, again, it's like a feature transformation that can change the number of features too. You can think about different ways of how you want to compute this big matrix. So this matrix here will always be of the size of the, in our case, like a 6x6 matrix, but you could extend or decrease the feature space. And yeah, these are learned. So this is very important because then, actually, it's sort of also interesting to think about certain exercises. So I taught a class on generative AI in the spring, and then one homework problem was sort of design me WQ and WK so that you extract a certain entry. Now you can sort of think about how you do that. And then you could also think about now create a matrix that extracts the sum of two entries. And it turns out actually that mapping is numerically quite unstable to give you, which means that in practice people use what's called multi-head attention. So they actually have different of these attention mechanisms that extract different pieces of information. But it's one of the core blocks. And again, to our theme here is like, now you don't define which dots are connected. You define the difference between the nodes and the features. And then you hope that there will be some important connections emerging. And also this is invariant of the number of elements in the sequence. And it's also permutation equivariant. Right? So if I have like let's say we delete one of these nodes here, our WK and the WQ are still useful because they only apply to the feature dimensions. And the same for the V matrix here as well. That's why they can react to different sequence lengths. And that's also why, in some sense, they are also permutation equivariants, which means that in language, for example, you need to have something called a positional encoding. Because in language, actually, the order of words does matter. So and anyway, that's something to yeah, to keep an eye on. Okay, so what we've seen in the transformer block. So then actually, this is just one little block of quote unquote the transformer. So you have this self-attention mechanism where you give it like the x times wq, x times wk, x times wv, do the attention, you get some z, and then you do some other things that we actually need to still define, like residual and feed forward and all of these different things. And then you get some output. So this is a quite more elaborate way of building and mapping an input to an output than just one layer of a multi-layer perceptron. In practice, what you actually have here is called a multi-head attention. Think about it for now as just dividing this thing up and having a few different feature channels. Okay, that's not the hard part. In language models, what you actually have here also this attention matrix. So basically this matrix here. You don't want your language model to look ahead in time to predict the next word. Actually, you want to constrain it to only look at the information presented in the sentence so far. So what you do there is you mask it. You have a matrix that is like lower triangular is 1 and upper triangular is 0, and then you do a pointwise product with it. That's what you use then for language model when you want to be autoregressive. But yeah, that's pretty much the transformer everyone's been talking about as a sequence of basically also an add-on to a GNN, fully connected network. So you can think about, okay, computational costs. There's some computational accountants here probably that are already scratching their heads at how can this be a good idea? Because now everything scales squared in the number of input elements of the sequence. That's why we are being charged per token. And yeah, there are some tricks to make like low rank and other things, other ideas work in this matrix. But what's hard actually, and you can see that here. So even if these connections here are low rank, you apply this nonlinear softmax transformation, and that's the trade-off now. You can make it low rank, but then you're not really getting the real thing. And otherwise it's sort of impossible to get this fully nonlinearity captured. There was a question, yeah. So you don't need to define the connections and the weights. I think that's probably the biggest advantage. I mean, advantage in the modeling flexibility. Because in a sequence, you don't, or in the Q-tip example exactly now, it should pick up on, given an image, these attention matrices should pick up which pixels are actually the important pixels to have the tips. And if you twist the image, it should pick up on that as well. Yeah?
To my understanding, it's like if you have a graph that exists already,
yeah,
then you can apply a graph neural network.
Yeah.
But if you don't have a graph data, you have any other kind of data,
yeah,
then you use the transformer.
Yeah, you could. But even if you have graph data but don't know the graph, you could also think about making up a similarity. It's actually very similar how you would compute a graph from some black box data. You would think about it like, how do you judge if two features are similar? You have different ways, and you do this manually. And there are definitely cases where you would want to do that. Because again, we talked about the no free lunch theory. Maybe we want to build in prior knowledge. If you have it, then you do it. Because these things, are not cheap to train last time I checked. Yeah.
I'm pretty sure like there's the advancements in transformers, like DeepSeek, although they have like very efficient structures for that's like the inductive bias.
Yeah, I mean, if you ask me, like one of the reasons I think people are interested in transformers is also, which unfortunately we will not talk about too much, at least on the slides, is the hardware component. So the hardware is very much optimized for these type of operations. And that's a game changer because there are models I would personally like more, like state space models and Mamba models that are just sequential in nature and therefore not as efficient on a GPU. But this is sort of flop-wise. I mean, this is a nightmare. But then efficiency-wise, with enough AI engineering and chip design, these things are actually quite fast. Yes, please.
So here, are we trying to normalize this matrix? That's why we there now.
Yeah, here that's sort of the embedding dimension. Yes.
Normalizing.
No, I think the decay. Sorry, the decay was just is sort of the, sorry, I don't have it here. So dk is the number of columns in the WK. Yeah? Yeah? Ah, oh yes. So this one just in the feature dimensions. Good question. Okay, Andreas, you had a question, and then we'll move on.
So this is related to what you said in the
Yeah.
beginning, where you talked about learning how to actually efficiently do matrix multiplications. Where I wondered, I didn't ask you then, you know, there is a lot of latencies by moving things through memory and so on and so forth, and if you say memory aligned, blah, blah, blah. So I'm wondering, you know, eventually you will get not compute bound, but formulation bound,
Mhm.
and so on and so forth. Is this something that's embedded in these things, or are
In
they
the
just-
transformer?
No.
Oh.
Matrix multiplication thing, where you talked about.
No, that was, I think, purely in terms of flops.
Okay.
Yeah.
So you have to be.
But, you know, once actually, maybe we'll get to this, but one thing I will say for now is that you can define the reward any way you like, right? So you could think about, you know, runtime as the reward or as part of the reward.
Yeah.
Wall clock time with a certain compiler on a certain hardware, something like that. Yeah. So it gives a lot of flexibility, and the algorithms may be different. Okay, one last question before we move on. Yeah.
On WQ and WK, W matrix, you have to compute them from the data.
Yes.
So you optimize for what?
For the entries of WK, QK, and WK, WQ, WV. These are weights, we call them, later on we'll just call them abstractly theta, and they'll be trained with, let's say, stochastic gradient descent over input and output pairs.
What did the objective function?
For transformers, well, actually, that is one that I'll introduce. It's just a standard cross entropy loss. Okay, good. Layer design takeaway is that with that design, we can like highlight connectivity and encode whatever invariances we have. Okay, so again, it's very problem specific. I wanted to show you a few options, some succession from very simple to very modern, and hopefully in a coherent way. So now let's go deep. So here is sort of my mind chart of things, and hopefully not too surprising. So the first thing you could do is you could just concatenate the layers. So let's call the hidden features now H. And so H0 gives you H1, H2, H3, H4. And each of them, for simplicity, just has our baseline model. Okay, that's sort of the old-fashioned way of connecting things. We'll talk about ResNets. We'll talk about neural ODEs. And especially in recent time, I've been interested in neural SDEs. And in some sense, one of the tensions and things to keep in mind is that we'll show you that in some sense, width enough is sufficient if you go sufficiently wide. So why even go deep? But then, of course, there's like a practical evidence and actually also theory that going deeper could be more efficient for some problems, if you think about a given compute budget. Okay, so the MLP just is a composition. You have a certain number of layers that can be discrete and finite, let's say. And one of the issues that you'll run into, and that's been sort of the 2010s, mid-2010s, is that people were able to build very impressively deep MLPs, like tens of layers, like AlexNet and all of these ones. And it's a miracle to me how they even trained them and how they designed them so carefully. Because when you make them very deep, this gets really hard. Because basically, if you think about just taking an existing MLP and add one more layer, the whole thing may completely change. So people call this the exploding vanishing gradients. Vanishing gradients, by the way, is what optimization theory tells you to do. You want to find a stationary point, so vanishing gradient is good. But there we mean that the gradient vanishes in a point that you're not happy with and you don't find a way to improve. Let's say everything gets multiplied by 0 and that's a stationary point, okay? So this then motivated the residual connections that we're going to see. But these multilayer perceptrons, they have a very rich theory. So you can have classical results like so to give you a taste. So if you have any sigma that is reasonable, in this case non-polynomial, then you make this architecture. So it's a single hidden layer and then an outer layer that is basically enough to fit any reasonable function. Okay. Now, of course, this is an existence result. I'm not telling you how wide does the network have to be, and also not telling you how hard it's going to be to find those weights. So that's always something to keep in mind. And also, when I'm reading papers, then it's sort of good to see how they actually use this result in practice, because it's sort of sometimes used as a wild card to get out of jail free card, where you say, well, I have a neural network, I should be able to do this, but then it's actually much more about also studying how do you make a decision about the width, how do you find this parameter, and then how do you solve the optimization problem so that you actually know that you find the width that can get the job done. Okay, and yeah, there's newer work that says that deeper networks are exponentially more efficient in certain sense. So think about it as you have a limited compute budget. Should I go wide or should I go deep? And then this clearly is like an interesting question to answer. And there's like a little bit of a gap because in theory, yeah, just making it wide enough should be okay. But in practice, oftentimes it's a deeper architecture that wins. Okay. But just to give you a sense. So a big breakthrough, I think, was the residual network. And the very innocent change they made was here to add what's called a skip connection. So rather than, so in the standard perceptron, you don't have this HL plus. So now this has pros and cons. You cannot so easily change the number of features. Sorry, you cannot change the number of features because otherwise you cannot make this addition. So this is a constraint on the architecture. But it turns out that with this little trick, you can actually train networks in hundreds of layers all of a sudden. And then in 2015, this was sort of the breakthrough paper where suddenly these were like knocking multilayer perceptrons out of the park. And the way they did this is really by going really deep, hundreds of layers. In the 2015, there's a lot of computational challenges that people had to overcome. One way to quickly think about why this could be a good idea is to think about what the gradient flow would look like. So if you would differentiate this for H sub L, then you would get something like an identity matrix plus a Jacobian of your layer. And that identity matrix, if you think the layer maybe is not doing that much, is making sure that sort of the sizes get relatively preserved and nothing gets killed and blows up out of proportion. Okay. Then also in that time, people have actually compared like what does actually the loss function in interesting directions look like for a normal network versus a ResNet. And they looked very different. I don't quite think you can always make a judgment, but I think I would find the bottom one nicer. A bit worrisome that it has like a lot of flat regions, so where maybe it's actually good to be a bit more bouncy. But yeah, definitely here is a point to make that the choice of the network architecture, and these were like sort of similar sized networks, can actually make a big difference on the optimization, which means that we, again, here, it's not just an optimization problem where someone gives you the problem, you need to solve it. Your choices in the architecture can make a big difference. Okay. So let's talk about one of my favorite topics, continuous time deep learning. So when you look at the ResNet, then it's actually quite obvious that there was something missing, namely a small time step. If there were a small time step, then you could think about this as something that looks like a forward Euler of something else, like an ODE or so. And actually, these ties, even in the previous wave of deep learning research, there are some architectures that today I think you could have branded as a residual network, where people try to learn time integrators for time series data. Okay, so it's a philosophical sales pitch, but if you have that mindset, then one thing you could say is that you could set the time step size delta t to 0, and now have an object that maybe we can apply some math to. Because now we have a continuous object, there's lots of theory that you can use, and actually also some methods. So that was sort of the starting point of what quickly became known under the term neural ODE. Because then neural ODE basically means that it's an ODE where the right-hand side or the dynamics is learned. So this is a mental picture. So rather than having a finite number of layers, you actually have a smooth evolution of a trajectory where the dynamics here are governed by an ODE, whose right-hand side depend on some trainable weights. Okay, you can now think about the width, or the depth of the network being loosely tied to how long you integrate the system, although scaling could be an issue because you're learning all the entries of the dynamics. So sometimes things can move faster than other times. But when you have this mindset, I think the appealing part that got people very interested in this line of work is that now you can, first of all, leverage ODE solvers. So rather than you deciding on how many layers you want to put, maybe have an adaptive time stepping method that makes a choice for you. You can analyze the stability. Like, for example, people were very interested back then in adversarial attacks. So I changed my input feature slightly, and now I don't want my network to go into a completely different direction. It's quite hard to do for a discrete network, but a little bit easier to do for an ODE. And other things, and I'm going to show you a few. So, but the depth now really is a continuous parameter. So the little t sort of used to be the layer, but now it's continuous. Okay, so as an educational moment, I should take the opportunity to talk about like some things that people have now realized were not so true about neural ODEs that people were excited about. And that relates to the memory cost. So there was a claim initially that neural ODEs have a constant memory cost. And by that, I mean that the memory cost doesn't grow as you add more time steps. And that's, of course, not true. And I think it's good to discuss this for a little bit so that we actually understand why we sometimes run out of memory on our GPU as the network becomes deep. So in order to compute network weights, we want to do something called gradient descent. And in order to do gradient descent, you need to compute gradients. And when you want to get a gradient of a continuous model, the way you do this is you run your forward model. This is the first row here, forward in time, evaluate your loss, get a gradient of the loss, and that you feed into something called the adjoint equation to go backward in time and get you the gradient for the weights. So that whole process is summarized in these three ODEs, solved now backward in time. So you have A as an adjoint variable that goes backward in time, the G as a gradient that goes backward in time. And in the neural ODE paper, the proposal is to actually recompute your state backward in time, because you see that the H is an input to all of these Jacobians. So it's not enough to just know the hidden features at the beginning and at the end. You need them wherever you evaluate your adjoint in the backward path. And that's where differentiating ODEs runs typically into memory challenges, because either you need to store them or sometimes recompute them. Recomputing them backward in time is a great idea if you're careful. But if you have a neural network that you're training, you may just be very challenging your luck a little bit to know that you're always safe here. So I'll show you that. But that actually was one of the claims that is not turning true, because in order to do that, you really want a network to be backward stable. Think about a simple case where your network learns a diffusion process, very forward stable, but you don't want to mess with this backward in time. So either you make sure that this does not happen by designing your F function properly, or the safer thing, and I think that's a standard practice, I have to check with Andreas whether it will be checkpointing. So you save a few snapshots, and then from there you compute forward in time. Okay, a little bit more compute, but much, much safer. But yeah, when you use neural ODEs, sometimes you need to be careful, because some software actually will implement this by default, and you need to deactivate that in case you run into any issues. So it's good maybe to keep that in mind. Another discussion we could now have is about optimized discretized versus discretized optimized. So of course, I mean, we go to continuous time, but then really in a computer, there is nothing like continuous time. You will need to discretize at some point, and you could do comparisons. So this is one result from the UT group in Austin, from George Biros's group, where you can ask, okay, so should I discretize first or should I optimize first? It depends who you ask, really, for ODEs. If you ask me, I would discretize first, which means, I basically take my ODE and I get another finitely number of layers, and then I do backprop. That's very simple with automatic differentiation and has a benefit that you always get a gradient that is accurate for what you discretize. Maybe not the true ODE, but this is machine learning. So the true ODE is just a guiding principle. But yeah, in a neural ODE framework, you would do optimized discretize. You would actually compute the adjoint backward in time. And that is nice because you can use adaptive time stepping and other things, but sometimes the computational costs are a little bit more because you need to actually solve the forward problem well to get a meaningful update direction. And yeah, it's up to you. For ODEs, it's really up to you. But what that paper at least showed is that in terms of what you care about, which is how well do you fit the training and the test data, you can have more bang for the bucks if you do the latter. And it's much easier to code. So hopefully that's a little sales pitch. Yeah, so say you really want to save all the memory, then here's a fun thing you can do. And that's actually was sort of our intention when we started looking into continuous time models. So you don't start with a ResNet, make it continuous, and go back to a ResNet. Well, then you're just running in circles. That's what we've done so far. What's actually a more intriguing opportunity is to take a ResNet, go to continuous time, and then change the ODE to your advantage and go to something that is better than a ResNet. So it turns out you could do that. So for example, like who tells you that you could not just do a second order time derivative? This is machine learning after all. The rule of the game is just, at the end of the day, produce a network that generalizes. Physics, no constraints for us, we can do that. And it can have some advantages because if you have a second order dynamic, you can use something called the Vallée integrator or leapfrog method. And this system, if you pick the F now carefully, for example, in this way, where you tie the weights, then this is reversible. So you can just do some algebra. You can see, you can solve this forward in time, you can solve this backward in time. It's a hyperbolic system. So information gets preserved. Nothing blows up in the forward, nothing blows up in the backward. And now you can save memory. Okay, now you can really fulfill the claim of neural ODEs. And you could also do this in other ways. You could do a Hamiltonian network where you have a very specific way of updating two parts individually. And what was interesting back then, and actually these papers were out before the neural ODE paper came out, is that think about in 2018, we trained a network with like convolutional network with 1,200 layers on one GPU, because you didn't have the constraint that you actually need to store anything. You solve the forward, you solve the backward, and you have your gradients. So that is a safe way if you're interested in saving the memory for neural ODEs. You design a forward-backward stable system, discretize it appropriately. So here's important to use some geometric integrators so that that carries over to the discrete level, and then you can avoid all the storage costs. And it's okay in machine learning to do so because that model sort of, in quote unquote, is fake anyway. I mean, people came up with the ResNet, sure, and because it works and not because that's the laws of image classification. So anyway, so these tricks, I think, shows you that you can go to the continuous place and then go back to a different discrete architecture, not the one you started with. Yeah, there are other fun parts, other fun you can have when you are in continuous time. So you can draw pretty pictures, and you actually can turn the whole thing into a PDE constraint optimization problem, where you think about the function u here as sort of like the labeling function. And the labeling function would preserve the label across the trajectory. So this is an advection equation. And your job now would be to find the weights of the initial condition, the W and the mu, and the velocity so that you minimize the loss at the terminal time. So now you can turn this into a PDE constraint optimization problem. Of course, nasty PDE, because this is a very high dimensional PDE. It's not like your advection equation from your PDE class in 2 or 3 dimensions. This is like as many dimensions as you have features. But conceptually, it's interesting because now that you understand that this is an advection equation, and let's say you're interested in creating smoothness or preventing things from blowing up, you could, for example, think about adding some diffusion to this process, make it an advection diffusion problem. And that's something I want to show you how people have done that in the past. So if you have a transport PDE, this is the deterministic PDE, and or the characteristics are deterministic, but you could have an advection diffusion problem where you have the Laplacian here. And if you pick the diffusion part carefully, you go from no diffusion to a little diffusion to actually quite a lot of diffusion in your classifier. So now the decision boundaries adapt, and hopefully your network outputs are more stable with respect to input perturbations. One animal that will come up every now and then is the Feynman-Katz formula, because of course you think now about this as a high dimensional PDE, and I told you, okay, conceptually, but you actually want to transfer that into a learning algorithm. You will not solve a high dimensional PDE then on a grid or so. There's a curse of dimensionality kicking in. So the Feynman-Katz formula is sort of, we'll use it probably on a daily basis to exchange a PDE to an SDE. And what it says for our example is, so rather than solving this PDE on a grid and in space, what you do is you solve an SDE where the drift depends on the velocity, and there is some noise added to do diffusion. And then you run a bunch of these trajectories, and you average their output. And averaging, for example, is for sure is good to smooth things out. And then the Brownian motion sort of also makes sure that you go into different parts of this space. So now this means that in that paper in particular, you're not just solving you're not computing one ResNet, which is like a forward Euler, but you actually have an ensemble of ResNets. So you run a few of these simulators. Think about SDEs as like a generative model that generates a bunch of possible outputs, and then you average, and that will converge in some sense to the PDE solution. That's the Feynman-Katz lemma. And the Feynman-Katz lemma is also nice now that we have this out, and I'll stress it a few times, is that for a transport equation, we can describe the solution by the method of characteristics, which turns the transport equation into an ODE. And then you just need to integrate ODEs, which you can do in high dimensions, whereas solving a transport equation, you can't. And so you really want that analog for advection diffusion problems as well. And that's given by the Feynman-Katz formula. We can also check, final thing I'll say for now, if the sigma is 0, so no diffusion, that should give you back the same thing. So it's really like an extension of the method of characteristics. Yeah, this is a very important formula when you want to study the mathematics of deep generative models or other deep learning techniques. So we'll use it, and you'll get used to that. Cool. Yeah, so this brings us to neural SDEs. So now we are in continuous time already. We have seen ODEs. Now, if you add a Brownian motion to this whole thing, now you have a stochastic generator. So you start with one input feature, and the longer you run this, the more noise will be added. And you can sample from the predictions. So again, it's an extension of the neural ODE. So if the noise is 0, then it's just an ODE, and otherwise it's stochastic. And I think the biggest use case for us, I mean, there are some real-life applications of where SDs are important, like financial markets or stochastic optimal control, which we will see on Thursday. But one of the big use cases is generative modeling. So in generative modeling, for example, image generation, you actually sample through SDs. So the drift term will be learned to some extent. That's the training part. But when you generate, you get a few SDE predictions, which is why you will get different outcomes every time you ask. So you get a few different images. Yeah, Andreas?
Do I see this as some type of UQ on top of it?
Sorry?
Do I see this as some type of UQ on top of it? Or
Yeah, I mean, you're learning a distribution. So it's a generative model. So you actually learn not a point-to-point prediction, but you learn a distribution. Again, generative models for me is just a way to represent distributions.
For sure, but in general, your samples would be sort of deterministic in the sense that, you know, you transport them and that's where your sample is, but now you have a key.
Yeah. Yeah, you get more than one sample. So in UQ, this is a very good way to define or to use AI in inverse problems is through SDs. Good. Okay, so this is, we talked about layers, we talked about how to connect them. Let's talk the final piece I promised, loss functions. And I'll keep this relatively short, but hopefully informative enough. So of course, the first thing you could do is just the least squares loss. Fine, we've seen that already. Actually, you could formulate that as an expected loss and an empirical loss. This distinction, I want you to remember for tomorrow morning. I said we'll dwell on that. They're not the same. We've seen an autoencoder loss. So this is the classification loss. This is a cross entropy, where in some sense your network produces something, then you make it a vector of probabilities, if you will, like an element in the unit simplex, and then you compute the inner product with y and the log of that vector. So this is really the cross entropy. Think about it. How well does the probability vector y and the probability vector p have the same information? So it's related to the mutual information between the two of them. And for GPT, what you do is you actually have a similar thing where you have a conditional distribution. So given all the previous stuff in the sentence, you predict the probability for the next token in a dictionary. So you think about 50,000 elements in a dictionary for the English language, for example. For each of them, you get some probability, and then you pick the one that is actually turns out to be true. So that's the same thing. To look a little bit more under the hood, so what do you do in the cross entropy? A little exercise. So let's say you have the outputs f, and actually they're not logits yet, they're just any output. Then you do the softmax transformation that we've seen in the GNN example, or in the transformer example. So you exponentiate and then you divide by the sum. So these ones now are in the unit simplex, the p's. And then when you compute the cross entropy, this thing beautifully simplifies to a log sum x plus a linear term. And I'm showing you this because log sum x, you may have seen it in a convex optimization course. It's a nice convex function that is non-quadratic. It's one of the go-to examples there. And we actually know what the Hessian looks like. It's a diag P minus PP transpose. It's a symmetric positive semi-definite matrix for every P. And we'll use that exactly tomorrow when we talk about Gauss-Newton approximations of the learning problem. So this is one example where you actually, and actually many of the examples from this, from the previous slide, sorry, are convex functions in F. And that I think will also be important when you talk about learning algorithms and optimization algorithms. It's not that there's no structure. Sure, in the weights, it's a non-convex problem, but oftentimes actually in the prediction function, it is convex. And here's for the log sum x, and we may go back to that slide when we talk about Gauss-Newton tomorrow, an example where, yeah, you have a convex loss in F. So if you had a linear model, this would also mean that you have a unique minimizer, or you could hope for like a valley or region of convexly connected minimizers. It only comes from the weights. One more question, yeah? Over the training data. So sorry. So here, this is the expectation over labeled XY pairs. Yeah, usually IID samples from some big data sets is what we would assume. Yeah, good question. Okay, Okay, there are other ways to have loss functions. We're not going to talk about GANs. Finally, we don't have to do that anymore because they're better models. We're not doing VAEs. Score-based denoising we will talk about, and pins also we'll talk about. So it's just, many other options. It's very specific about what you want to do. So we're pushing on time. I should probably sum up. So, okay, so we have set up a learning problem now. It's minimizing the expected loss function. And that loss function depends on all of the ingredients. So it depends on what architecture do we choose for building a layer, how we make the architecture deep, and what loss function we pick. So these are three elements. We're going to do a simple example tomorrow with our baseline multilayer perceptron and a cross entropy loss. And then we'll see how far we can get there. And then later in the course, when we talk about AI for math, the network architectures will become a little bit more involved, and the loss functions may become more involved, may have partial derivative operators in them or other interesting things. But it's always the same principles that you build an expected loss function, and then you try to minimize that. And yeah. So for today, we've covered a little bit about intro to machine learning and then how to make a network. And then the next 3 lectures are going to be about optimization. How do we actually compute minimizers? Let me check if there were questions here. No, doesn't seem to be. We have a few more minutes. I think we were pushing a little bit on time. Sorry about that. But I'm around if you want to chat. And hope you'll be back tomorrow. Oh, yeah.